Good morning. Here are yet again for another lovely session of CENG 3325 Structural Analysis. Today we're going to be looking at the forces inside members. And I have a few objectives here today. First, I want to explain the relationship between load, shear, and moments along a member subject to bending. I want to draw the shear and bending moment diagrams of beams and other members subject to bending, and explain the meaning and importance of shear and moment diagrams and functions. Okay, so this is going to be a bit of a review for mechanics materials, but it will serve as a very useful introduction to some of our later studies through the semester. So as a review, let's first look at the sign convention of shear and bending moments. So I know this is a bit of a review, but it never hurts to mention. So for shear, here, if I look at the internal forces of shear and moment, let's look at the sign convention here. And I'll draw this, I'll draw shear on the left and moment on the right. Here, so this would be V, and this would be M. Now, in terms of sign convention, let us review what positive shear and positive moment look like. Well, positive moment is easy. That's a moment that causes something to bend in positive bending, which of course, if you can never remember what positive bending looks like, it's the happy bending. The smiley face bending, lovely. Then positive shear is where you have a member or an element that is positioned like this. So you have an upward shear force on the left side and a downward shear force on the right side. So when students are first learning shear and bending moment diagrams and statics, this can be a bit confusing, I know. Because it's something students always struggle with when they first learn this stuff, because they see an upward arrow, they want to call that positive. They see a downward arrow, they want to call that negative. But when doing sum of forces on an end, sure, that'll work out. Upward will be positive, downward will be negative. But in terms of whether an individual beam, an individual section of a beam, is in positive shear or moment, you have to use the sign convention here. Positive shear, the state of positive shear and the state of positive moment are defined by two arrows and their relative directions. And so it's not enough to have a positive arrow, you must have a positive shear arrow on the left side of a member and a downward shear arrow on the right side. And when I draw this, I'm considering these as differential elements. So elements of very, very minor width to the point where the change in shear on either side is minimal. Okay, so there are three methods to find shear and bending moment diagrams. Three methods, and we'll go through some of these. The three methods of shear and moment diagrams. And the first one is one we've seen before. Well, actually something we were just working with in terms of trusses, and that is going to be the method of sections. It's going to work exactly like trusses. Well, not exactly like trusses, but same in principle anyway. We cut a imaginary line across the beam, and we look for what forces are revealed inside. Then we also have integration, which will be much more important. Maybe I can put a few notes on these, and inspection. So let me put a few side notes on here, just my thoughts on these. This is similar to trusses, what we've already seen. Similar principle to trusses. Integration is very useful for finding deformations, because once you solve for deformation via integration, or once you solve for shear and moment via integration, it's very easy to also integrate further to get the deformation. Useful for, let's say again, for finding deflection. And inspection, this is more just based off of simple area methods, and it's a simple area method. It's often, for quick and dirty design, this is often the easiest one. So if I have a relatively simple system, a relatively simple beam, usually I'll actually end up using inspection, just depending on the complexity of the problem. But I want to look at each of these in turn. So let's consider our three methods of V&M diagrams. And the first one is going to, of course, be the method of sections. So, the method of sections. Now, again, we know basically that if I cut a beam, there will be three forces revealed. So let's see how the method of sections that we looked at previously for trusses can be applied to beams. First, I'll look at this as a method of sections at a single point, and then I'll look at the method of sections at, say, as a function of x, cutting at a point x. Let's look at two different problems. So let's say you have a beam like this here, and maybe it's simply supported like this, and let's say it's simply supported like this here, and we have reactions. Let me define a few points. I'll define point A at the left, point B at the right, and some point C in the middle. And then showing the reactions on here, I have AX, AY, and BY. And then let us say that there is a 10 kip force between A and C. And we want to find VC and MC, the shear at C and the moment at C. And then we would also need the dimensions here. And let's say this is 4 feet, 3 feet, and 5 feet. And let me go ahead and label my A forces, my A reactions. So this would be AX and AY. AX and AY. So we want to do this, and solution, I'm going to gloss over finding the reactions. That's just basic statics, trivial statics. So solution, if I want to get the reactions, that's trivial. I can just, if I want to get BY, I can solve for the moments about A. AY, solve for the moments about B. Sum of forces in x direction gets AX equal to 0. That's trivial. So 1, get the reactions. And if you do this, you will find that BY is equal to 3.33 kips, and that AY, upward, and that AY is equal to 6.667 kips, also upward. Now, what I want to do is, this is a method of sections problem, so instead of cutting across several members, I'm going to cut specifically at C. So this problem here, again, is just to illustrate the basic concept here. So let's try cutting at C. What do we have? Well, if I were to draw this member now, let's draw this isolated member and look at all of the forces that are keeping this thing in equilibrium. Well, we have our 6.67 kip force here. We have BC, which would of course be the shear at C. Let me draw that a little more like an arrow, like this. Now, question, why did I draw it downward? Well, yeah, we could do that, but really what I'm assuming, I just went ahead and assumed positive. Usually what I do is when I make a cut, I generally assume positive shear, and then if I get a negative, I just know I have negative shear there. No biggie. Okay, and then I'll also draw my moment as assuming positive here, MC. Then we have a downward force of 10 kips. And it might be nice to have my dimensions on there. And so this would be 4 feet and 3 feet. 4 feet and 3 feet. So this one isn't really going to be too bad. This one's fairly simple because I'm solving for at the shear and point rather than the shear and moment as a function of x. So it's fairly straightforward. Now let's go ahead and get those. So if I do a sum of forces in the y direction, I will have 6.67 kips minus 10 kips minus VC is equal to 0. And that produces that VC is equal to negative 3.33 kips. Is equal to negative 3.33 kips here. So it's actually, we're actually going to have negative shear here. So in truth, this shear arrow is actually going to be pointing upward. So we got the shear at C. Now let's go ahead and get the moment at C. And I'm just going to go ahead and do a sum of moments about C. That'll be the most convenient way to do this. That way my shear at C won't generate any moment in my calculation. Some moments about C, counterclockwise positive. And I will have, let's see, negative 7 feet times 6.67 kips. And then plus 10 kips times 3 feet. Again, negative because clockwise, positive because counterclockwise. And then plus MC, and all of this is equal to 0. And then finally, MC is equal to 16.69 kip feet. MC is equal to 16.69 kip feet. Here. And so we have both positive shear and positive moment. So if I were to actually draw out the, maybe I'll actually draw out some blocks here for the moment and the shear. If I were to draw these out, I would have VC is negative and MC is positive here. So it would look like this. Again, we're looking at little differential elements here. So by differential elements, I of course mean these things are of negligible size. And I think I want to fix that MC because it looks way too, or that VC, it doesn't look like a parentheses. Give that a little more room to work with. And this is negative. But then the actual direction of the arrows will be as follows. This is going to be negative, so it means we actually have a downward arrow on the left and an upward arrow on the right. And we have positive bending MC like this at 16.69 kip feet and 3.33 kips. Questions on how I got any of that? Questions? And yes? Go back to, oh, sorry. Thank you. Questions on how I got that?
As far as the moment around C, let's see if some of that first one.
The sum of moments about C.
6.67 kips, that's 7 meters away. Here you had it negative.
Yes, because if you think about it, it's if I'm summing moments about C, the question is why is this negative? Well, if I sum moments about point C, this force here is causing a clockwise rotation about point C, so that is a negative rotation. So remember back, I know it's been a while since statics, but negative, of course, clockwise negative, counterclockwise positive, but that's okay. That's why we're in class. We're here to learn. So, other questions? Okay. So that's nice and all. This problem is nice and all to illustrate the idea of internal forces. To illustrate, and in fact, there's actually one other thing I could show here. I could show that there is an NC here, but that's clearly equal to 0 because there's no horizontal forces. But so these are the 3 internal forces that can exist in members. Now NC in this particular one is equal to 0, but later when we get onto frames, we'll see that that is often not equal to 0. So, but moving on. This is nice and all, but what I'd really like, if I want to truly understand a member, I don't just want to cut at some single point C. What do I really want to do?
Make a function.
What I really want is a function. Yes, what I really want is a function. I want some function that's going to say, here is the shear, not just at one point. I mean, we could do that if you were really determined and algebraically challenged, I suppose. If you really were terrified of algebra, you could go and just do a method of sections on a beam every every half foot or tenth of a foot or whatever. And we'll actually, that wouldn't actually be so different from how some finite element programs effectively operate. They basically often divide beams and members into tiny little chunks, but that's because those are usually systems that are statically indeterminate, maybe even undergoing plastic deformation, so you need very complex math. So instead you divide these things into little tiny chunks that allow you to make assumptions, but that's neither here nor there. So next, let us consider shear and moment functions. shear and moment functions. So the key here, the big key to the success of this is that you're going to have to cut at X. What I mean by this is that you want to make sure wherever your cut line is, that is the X in your equation. Also, you want to keep your origin constant. It's very tempting when doing beams to say like maybe redo X every time you cut it, because oftentimes the tricky part about this is oftentimes we'll end up cutting a beam and we'll have to do a cut several times because of discontinuities in the beam in the load function, and so anyway, so we'll need to we'll have discontinuities in the load function, and in turn we'll need to cut several times. And it's tempting, it's oh so tempting to redefine X as 0 every time you cut it, but we really need to keep a consistent origin. So for beams anyway, now for frames it's a bit more complex, but for beams anyway, we usually just keep the left end as the origin. Or X equals 0. Okay. So here, when do I need a new free body diagram? Oh, that's another key question. When do I need a new free body diagram? Well, this is all based, we'll see later that we've already mentioned that one of the methods of getting these is integration, and that should be a key. Discontinuities in load are the key. In load are the key. So, anywhere you have a discontinuity, you'll need those will form the boundaries between your zones of analysis. So, where examples of discontinuities, these are things where, for example, distributed load changes, changes, stops or starts, where you have concentrated forces, concentrated moments, supports, hinges, etc. Discontinuities. So we'll look at a few examples of this on the next slide. Anywhere you're going to have a discontinuity in loading. So again, all of this comes back to basically all of this is fundamentally coming back to calculus, that the you can't integrate across a discontinuity. That's the important thing to remember. You cannot integrate across a discontinuity. Remember all that stuff in calculus where you learned about, oh, is this region continuous but not differentiable? Is it differentiable? And so on and so forth. You thought you would never see that again? Well, here it is. You thought maybe there would never be a practical application of it? Well, here it is. So if you ever are looking for the practical application of it, this is one of them. If you ever have, these represent discontinuities in functions, and we cannot take a derivative or a integral across a discontinuity. So let me show you what I mean by this. So for example, examples of discontinuities. Examples of discontinuities. So let's say we have a beam here. Now, let's look at something very simple. Let's say we had a load function like this. Well, maybe we did something, I'm going to try to do like a nice linear load or something. Nice and linear. Oh, whatever, it'll be continuous declining load. Sort of a parabolic load. There we go. How many discontinuities are there in this load? There are 2 discontinuities. These discontinuities are here and here. 1 and 2. So we can, basically that means we can integrate from 1 to 2. That makes sense. So we basically just have one zone of integration. Or if we're doing the method of sections, we only need one free body diagram as a function of x. Fairly straightforward. But what if we have something like this? Let's consider something like this here. Let's look what happens if the load function changes. Maybe it could be simply supported again. But let's say I did something, kind of like the, let me go back to red. Let's say I had something like this. Maybe this is level and then it's suddenly, maybe it's level constant. And maybe it's like this. And then it's like this. Okay, there, I got my discontinuity shown. So from here to here it's level, but then it becomes more of a trapezoidal loading. So how many discontinuities do I have? 3, yes, 3. Here I have 3 discontinuities. So that means I will need 2 zones of integration. Or I could just call them zones of analysis for now. So when we're doing method of sections, zones of analysis mean free body diagrams. And when you're doing integration, it means 2 boundaries of integration. So I could have points 1, 2, and 3. These are my discontinuities. And then I would have one integration from 1 to 2, and then another integration from 2 to 3. Again, discontinuities. Okay, so let's look at something else. What if I had another beam here? And then something like this. Let's make a really fun beam. Let's do something like this. How many discontinuities do I have now?
5.
Whole bunch. Let me just count them. Let's see, I have one on this end because there a load starts, a load function starts, and there's a reaction. Then I have one here where a load ends. Here I have one where a load begins. Here I have one where a load ends. Here I have one where a reaction occurs. And really, in this perspective, a reaction is just a force. If you think about it, a beam floating in space, a reaction is nothing more than a force. And then I have 6 here, where the member end force is. And really, even if I didn't have a force there, actually, let me make this really interesting. I'll go ahead and I'll move the load and put it over here, just for extra fun. 6 and then 7. The end of the beam is always going to be one of your discontinuities by definition, because the beam just stops there. It stops there because, essentially, mathematically, by definition, any point beyond the edges of the beam has 0 shear and 0 moment, just by definition. And mathematically, that represents a discontinuity. So here I'd have 7 discontinuities. Oh boy. Which means I would need 6 zones of analysis. So if I was doing this all by integration, I would have one integration from 1 to 2, one integration from 2 to 3, one integration from 3 to 4, one integration from 4 to 5, one integration from 5 to 6. Well, my integral signs look like S's. One integration from 6 to 7. Isn't that lovely? I probably didn't need to write all of that out. But it is important to be aware and mindful of source of discontinuities. So it's basically whenever the load changes. So that can be a point load, it can be a point moment, it can be the value of the load doesn't even have to change. As we saw here, mathematically, what would we call this function here? Remember from calculus? Huh? A headache? No, that's not that's not a good attitude. This is only Calc 1 stuff. This is easy. I would call that, remember from back to math, would this be, remember back to Cal 1, would this be continuous, differentiable, what would it be? Across the boundary here. No, I'd say this function is continuous. The limit from the left equals the limit from the right, and the value of the function equals there. It's definitely continuous, but it's not differentiable. So this is a continuous function. From 1 to 2, this is continuous, but it's not differentiable. Here we have something that's not continuous, but maybe that's not terribly important. But anyway, I thought, am I giving you flashbacks to calculus? Like, oh God, no! I promise not to forget C again. God, not the plus C, not the plus C. And guess what's going to come back here when we integrate? Anyway, plus C, yes, plus C. Okay, so example 2. I want to look at this method of sections as a function of x. Now I'm going to have a beam here. I'm going to show you a beam, but I'm going to go ahead and just give you the reactions because I think by now you know how to solve for reactions. If not, please see me after class. Or sorry, I should say, please see me during my office hours and we can discuss methods of doing that. Sounds a little less ominous. All right, so let's say this is going to be point A, pin support at A, and a roller support at C. And this thing's going to have a nice continuous loading across, at least nice until I get my hands on it. It's nice continuous loading across, constant loading. Yes, let's draw loads, happy loads. Channel Bob Ross. The joy of painting. Happy little trees. Let's draw a tree. And this beam is next to a tree. Yeah, this beam is next to a tree. Yeah, let's do that. This beam is next to a tree. Happy tree. There we go. There's your happy tree. Anyway, that'll have no relation to the beam problem. It's just next to a tree, a happy tree. And then I'm also going to have another point with a concentrated moment at it. And let's say this load is 2 kips per foot, and then the concentrated moment is 36 kips per foot, or 36 kip feet, I should say. 36 kip feet, and then we have dimensions here. Definitely need some dimensions. And the dimensions here will be 9 feet, 9 feet, and 6 feet. 9 feet, 9 feet, and 6 feet. Then the reactions. Again, I'm just going to go ahead and give these to you. We could solve for them, but I want to save a little time here because we had to save time for that tree. And so then AX is equal to 0, and AY is going to equal 18 kips if you solve for that. And CY is going to be equal to 30 kips. So we have all this, and we want to find the V and M diagrams. Find the shear and moment diagrams. So, unlike last time, we're not going to cut at a particular location. Instead, we're going to cut at X. And so the question I have for you is, how many cuts are we going to need to make? 3. We have 4 discontinuities. The end of the beam, the point moment, the support, and the other end of the beam. So 4 discontinuities, that means 3 zones of integration. The discontinuities, I really want to pound this home or drive this home, that the discontinuities represent boundaries. Put that big in your notes and put a big star over it and draw a happy tree next to it, because the discontinuities represents bounds of integration, or the discontinuities represent boundaries of analysis. Draw happy trees. Or rainbows, because, Or draw rainbows, because they don't have meanings about rainbows. Is that a Sixth Sense reference? Wow. So then, let's say step 2 would be your reactions. Would be get reactions. We already got those. Step 2 would be to cut at X. Let's cut at point X. And I'm going to first cut at X when X is less than 9 feet. When X is less than 9 feet. So X is less than 9 feet. We're in this zone here. And what I'll do is I'll go ahead and just draw a free body diagram there. And this section of the beam, this is going to be kind of interesting, according to certain definitions of interesting. First of all, it's going to be X feet long. So this beam is not going to be 9 feet long. The section that we're cutting out is X feet long. Ooh, that'd be wouldn't that be fun to do using trusses, like a cutout? Well, no, I guess the internal forces would be the same, so I guess it wouldn't be that bad, but that could be so much fun. Imagine cutting a truss at X. That would be so much fun. But anyway. But I guess that's basically what we do for method of sections and trusses anyway, so. Oh well, fine. I was trying to be evil, but. Alright, so I'm going to go ahead and show my forces on here. And we have 18 kips, and this is point A. Then we have our distributed load of 2 kips per foot. Of 2 kips per foot. And our end reactions of VC, VX I should say, and MX. VX and MX here. And again, I'm just going to go ahead and assume positive shear and positive moment. So now it's just a matter of doing basic equilibrium. Huh? Equilibrium. Oh yes, some may pronounce it equilibrium, somewhere perhaps. So if I just do a sum of forces in the y direction, I will get 18 kips upward minus 2 kips per foot times a length of x feet minus Vx is equal to 0. And if you solve for this, you will get not a fixed value, but V as a function of x is equal to 18 kips minus 2x. 18 kips minus 2x. So again, 18, that was just the upward force here. And then downward, I needed to take the total downward load of the distributed load. And it has a magnitude of 2 kips per foot, multiply a length in feet x, you get the total length 2x. And then solve that, you get 18 kips minus 2x. Next, I can get a sum of moments, and I'm going to usually do a sum of moments about x. The nice thing about that is if I did a sum of moments about point A, for example, I would need to include my Vx in there, and that would include the function that I already got, and it's not terrible, but I like avoiding that if I can. And so now, when taking into account distributed load, we need to go back to remember in statics that when doing balance of forces, we can replace distributed forces with their equivalent point loads. So the equivalent point load to a uniform load is going to be the total load applied at its centroid. And so the centroid would be halfway down. First, the negative x times 18 kips. This is the moment caused by the 18 kip force, again at point x. Negative because it is clockwise. Then plus 2 kips per foot times x. This is the magnitude of the total load. Again, just like here, the 2x. Now we need to multiply by the moment arm length, and that's x over 2. That's x over 2. For a uniform load, remember the centroid is going to be right at the center. If it was a triangular load, it would be 1/3 the length, 1/3 of the length from the base, etc., etc. And then plus mx is equal to 0. And if you solve for m of x, you will get that this is equal to 18 x squared minus, 18x minus x squared. So any questions on how I got that?
Why is it negative x?
Again, why is it negative x? If you have point x here and you sum moments about that point, this 18 kip is going to generate a clockwise rotation. The distributed load will generate a counterclockwise, clockwise positive, or clockwise negative, counterclockwise positive. Okay?
Sure.
And interestingly enough, what do you notice about these two functions?
Integrate that one.
Exactly, they're integral relationships. So now we can't directly get this by the integration of this because we'd still have that plus c on the end if we were doing an indefinite integral. But we can definitely see that there's some sort of integral shenanigans going on here. And we'll see that when we look at the, and that's a technical term, integral shenanigans. No, it's really not. But it goes along with happy trees, so I guess it's okay. All right, so there's that. But of course, there is a direct differential relationship. I will see later, of course, and remember from statics that the derivative of moment is shear. Okay, so next I want to cut at x when x is between 9 and 18 feet. So as a reminder, we don't reset the origin. We do not reset the origin. So it might be tempted to cut here and say, oh, this point here is now 0. No, we keep it at 0 here. That way our final piecewise function will be compatible. And you could probably get away with defining 3 independent functions with just doing the method of sections and making 3 independent free body diagrams, but especially when you do by integration. You'll have to use the values from the left end, or from one end of the right end of one zone of integration, as the boundary conditions for the left end of the other one, and they really need to have a consistent x origin. Otherwise, you won't be able to get the correct solution. 2, we're going to cut at x again. Where's our step 3? Sorry. Cut at x again. This time when x is between 9 and 18 feet. So let us look at, and again, I'll just go ahead and draw a little free body diagram. Happy free body diagram. And make it a little longer. And I'll have a distributed load here. And this is 2 kips per foot. And let's see here. We'll have our 18 kip force here. We'll have at B, this will be point B, we'll have our 36 kip feet force. Or our 36 kip foot moment. Then we have our V of x and M of x. Again, why did I draw them the way that I did? I assumed positive. Yes, I drew them the way I did because I assumed they were positive. And the only other thing I'd want on here is some dimensions. So I know this entire thing is x. I know this entire thing is x. And I know the distance here to here is 9 feet. It's a really bad 9. I know that's 9 feet. And then in turn, I know that from here to here is what?
X minus.
Good, just very simple, x minus 9. X minus 9. So then I'm just going to go ahead and do the same kind of thing I've done before. Sum of forces in the y direction is equal to 0. So I'll get 18 kips. 18 kips minus 2 kips per foot times x minus v of x equals 0. And then so v of x is equal to 18 kips minus 2x. Huh, interesting. What do we notice about that? It's exactly the same. Wait, so did I lie to you when I said we needed to cut it at a different location? No, I didn't directly lie to you. Maybe indirectly, but not directly. Let's get the moment, and maybe we'll divine a bit of the relationship here. That's a word we don't use very often. Gotta divine the relationships. Get a little divination rod, and we'll find out where we're going. That's very scientific. Anyway, no, please don't do that. So sum of moments about x then equals 0, and I will get again negative 18 kips times x. Then let's say we have I'll just have plus 36 kip feet. Where's my moment arm for my couple there? Shouldn't I multiply by times x minus 9?
Dimensions included.
But it's there, so it doesn't need I'm balancing moments. Don't I need a moment arm? But it's there. It's right there. So I need a distance, don't I? Oh right, yeah. It's already a couple. I don't need to I don't need to multiply by a moment arm. It already has one. Again, I'm just going over some common pitfalls. So anyway, I don't know how many times I see that on exams, even instructional analysis. And then plus, I need the moment caused by the distributed force, and that's plus 2x times x over 2, no difference from last time. And then plus m of x, the moment actually at x. This will then equal 0. And finally, I get m of x is equal to 18x minus 36 minus x squared. And so again, we see that there is a integral differentiation relationship here. There's some calculus shenanigans going on here. And so, but in turn, we also saw that previously, if you compare it to the previous equations, the shear is the same. But what is not the same? The moment's not the same. And really, this shouldn't surprise us. A couple is pure moment. A couple doesn't produce any change in the shear. A couple will produce a jump in the moment diagram, but it's not going to do anything to the shear diagram. It's purely it's purely a couple. It's pure bending, basically. Okay, so then next, I want to cut at x for the final zone. Cut at x for when x is between 24 feet and 18 feet. 24 and 18 feet. And I have a beam like this here. So let's have beam points A, B, and C. And I'll go ahead and show all the forces on here. Distributed load, happy distributed load. Nice happy uniform load going all the way across of 2 kips per foot. Then I have my 18 kip force AY. I have my 36 kip foot moment at B. And I have my 30 kip force, my 30 kip reaction force at C. Then I have dimensions here of 9 feet, and x minus 18. Because this entire dimension, the entire length of this thing, again, we're not cutting at the end of the beam, we are cutting at some location x, so that means that final dimension there at the end is going to be x minus 18. And then is my free body diagram done? I have my reactions. The internal forces, yes, the internal forces. I need the reactions at the end of the beam. So V of X, why did I draw it downward? Assume positive, yes, assume positive, always and always. And M of X. And M of X here. So if I then do so let's go ahead and do a sum of forces in the Y and a balance of moments. So sum of forces in the Y direction is equal to 0, and then that equals 18 kips plus 30 kips minus 2x, as we've established previously, minus V of X is equal to 0, and we get that V of X is equal to 48 kips minus 2x. Minus 2x. Then if I do a sum of moments at x, again counterclockwise positive, it's going to equal 0, and I'll get negative 18x plus 36 minus 30 times x minus 18 plus 2x times x over 2. Nothing radically different here. This, again, 18x, that's going to be the moment caused by our end force here, negative because clockwise. The 36 is just the moment caused by the point force, or sorry, the point moment or the couple. Then the negative 30 times x minus 18, that's the moment caused by this, with a moment arm length of x minus 18. And then plus 2x times x over 2, that is just the same moment caused by our distributed force. And if you go and solve for that, solve for m of x, oh, and then plus I actually need plus m of x. All this must equal 0. And if you solve for m as a function of x, you will get that this is equal to negative x squared plus 48x minus 576. Isn't that fun? Joy. Questions on how I got any of this? Okay. I will then. I want to finally summarize the shear and moment functions, and then show these on a plot as well. So we have v of x equals a piecewise function of 18 minus 2x, 18 minus 2x, and 48 minus 2x. Here when x is less than 9 feet. Here when x is between 9 and 18 feet. And here when x is between 18 and 24 feet. And then m as a function of x is going to equal, here, I probably need more room than that. On the next slide I'm going to show some actual diagrams. 18x minus x squared, and then 18x minus 36 minus x squared, and then negative x squared plus 48x minus 576. And this is when x is, same bounds here, less than 9 feet. Here x is between 9 and 18 feet. And here x is between 18 and 24 feet. Here when x is between 9 and 24 feet. Again, and we can, again, we are reminded of the integral relationships here. We're reminded of the integral and differential relationships here. We see that if we take the derivative of this, we get this, derivative of this, etc., etc. And so finally, I just want to show some actual diagrams. I did say get the shear and moment diagrams, so I want to go ahead and get that. So let's put the shear and moment diagrams. And what I like to do is I usually like to draw the load, and then underneath that the shear, and then underneath that the moment. So I'll have my load diagram, which is really just a free body diagram, essentially. So finally, V and M diagrams. Maybe I can call this, that's fine. Final V and M diagrams. The final V and M diagrams Here, let's see. We have this here. We have 2 kips per foot. Distributed load of 2 kips per foot, a reaction of 18 kips, another reaction of 30 kips, and an applied couple of 36 kip feet. Then I might want to put the dimensions on here for completion's sake as well. So this would be 9 feet, 9 feet, and 6 feet. Then I'm going to draw the shear under this. And these shear functions would be produced just by plotting the equations. So that, again, the shear and moment functions that I'm drawing here, these are just very straightforward plots of what we already have. So you just plot them like you would any algebraic equation. So we'd have, I'll have V in kips here, and M in kip feet. And the functions, you know, I like to put sometimes I like to put trace lines on here just to line everything up. We're reasonably lined up anyway. Oh wait, that's not lined up reasonably at all. Let's fix that. Nope, I really fixed that good.
Fix that good.
The fix is in. Alright, so let's go ahead and do this. I want a trace line from the couple. Basically, I like to sort of trace out my discontinuities, just to keep everything. I mean, these are sketches. They're not to scale. They're not exact, super exact, but I like to put a couple trace lines in. Again, those yellow lines there, those orange lines, they don't indicate anything. That's just to help me keep everything reasonably lined up. And so I'm going to have, I'll start off with a shear of a positive 18. And then by the time we get to point C here, points also, this is point A, B, C, and D. By the time I get to point C, it's going to drop down to negative 18. So it's going to go kind of like this. Hey, I actually managed to draw a reasonably straight line. And then here it's at 0, 0. Notice it's 0 for, interestingly enough, it's 0 for both functions. So if you put in a length of 9 feet into both these functions, you'll get 0 for both of them. So that makes sense. Then the 30 kip force will cause it to jump up 30 kips. So we'll end up at 12 kips here. We'll end up at 12. And then we'll distribute down, or not distribute down, we'll go slowly down to 0 at the ends. Then the moment, if you plot this, here, we start out at 0, and then we end up at point B here at 81.
That's a maximum, right?
That's going to be our maximum, yes. And it's going to be parabolic, again because of calculus. Then our moment is going to drop by 36 down to a value of 45. And this is interesting. I always find this interesting, and it's kind of hard to wrap your head around at first, but it makes sense when you think about it. Notice this applied load, what direction is the applied load? It's positive, right? But it causes a negative decrease, or causes a decrease in the internal moment. And the reason is because internal moments balance exterior applied moments. So they have to be equal and opposite. So if I apply a positive moment, I'm going to get a drop in the internal moment, because again, shear and bending moment functions show the forces that are interior to the member. They're the forces that are fundamentally resisting all of the external loads. Then we're going to have another parabola here that will drop down to negative 36. So we'll decline parabolically to 36, or negative 36. And then we'll increase parabolically back to 0. Something like this. And this isn't so important because we already have the functions, so we can just plot them. But interestingly enough, we do know that we'll see this more when we get to the differential relationships. the slope, because the shear is the derivative moment, notice that that moment should be the slope of, notice that the value of shear should be equal to the slope of moment. And so when this thing is horizontal, this thing should be 0. And when this thing is steepest, this should be at maximum, etc. So, but we will look at that in the next video. So, all right, that'll do it for today. Thank you for watching. If you have any questions, please let me know. I'll see you all on Tuesday, and as always, thank you.